our next speaker is Professor Xiaopeng Li from University of South Florida.
Thank you, Dr. Thank you, Xiaopeng. Let me see. How do I share my screen? Just one sec. Slideshow from the beginning, and I think to share the share screen and oh, actually, this is wrong probably.
Wrong monitor. You have multiple monitors.
Yeah. Let me do it again. Hope this time it'll work.
Vertical monitor, right?
Yeah. Sorry about. See. Let me see. So meeting control. Okay. Now, do I share my screen right now?
Yes. Yes.
Okay. Can you see my screen? It looks good, right?
Looks good.
So I'll just talk about some empirical study on fuel consumption and emissions for commercial automated vehicles with different headway settings. So our contribution is mostly on different headway settings. So this is work with my students, including Xiao Weishi and Han Dongzhao. And this work is sponsored by my NSF research. So I think, yeah, the previous speakers have talked a lot about the energy consumption in automated vehicles. And so, so basically the focus of this study is commercial automated vehicles that are already running on the road. They're not the lab designed vehicles. The reason we pick up the commercial automated vehicles is because they are already running on highways. And I think right now there will be a few percent of vehicles in US highways that have automated vehicle functions like adaptive cruise control. And their market penetration rate increases at a double digit every year. So we will basically look into longitudinal control, so-called adaptive cruise control, sometimes autopilot, sometimes RSS, basically the existing commercial longitudinal control, let's say ACC for this purpose. This is a basis for not only the low automation level that are the vehicles that are running in the road right now, but also higher level traffic automations as the technology progresses. So one special thing that we want to study is, for almost all ACC technologies that gives users to prefer or to select the preferred headway settings. So, you can, in addition to set up the following speed, you can set up the following headway, such as these bars. The greater the number of bars are, the longer this following headway is. There is plenty of studies investigating how adaptive cruise control impacts energy consumption, but it seems like how different headway settings will impact energy consumption. That is a really valid and interesting question. It has been ignored in the literature. So this study will address this problem to look into the energy impacts from multiple following headway settings. So, and this seminar is about freight and logistics. While we're using passenger cars to as a study subject, but the results are generalizable to freight and logistics. For truck platooning or truck and automated control, adaptive cruise control is still a foundation, and they share the similar controlled mechanism. And also there are lots of freight deliveries that are using light duty vehicles such as Uber Eats, Instacart, particularly in the pandemic season. And so in order to investigate the impacts, we use the automated vehicle facilities that we have. We have some commercial ACC vehicles. Although we retrofit them to our lab vehicles, but in these experiments, we use the manufacturer's default settings to reflect the commercial design logic, not our design logic. So we use actual GPS to collect the vehicle trajectories. So we have done a number of field experiments with different settings. So we have a lead vehicle that could be just a cruise control vehicle that we can set up a speed control profiles, and then we can follow it by one vehicle or two vehicles that are automated, that are ACC vehicles, and we can collect their trajectories, and we can use model to predict or estimate their fuel consumptions. We run multiple tests on the public road when the traffic is light, so we can keep the proceeding the lead vehicle's trajectories as we desire. So for this particular test vehicle, Lincoln MKZ, it has 4 headway settings, as you see here on the right. So the number of bars in front of this vehicle symbol could range from 1 to 4. 1 is headway setting, 1 corresponds to the shortest headway, 4 corresponds to the longest headway. So these are the trajectory data we collected in one set of experiments using multiple vehicles, 2 vehicles following 1 lead vehicle at different headway settings, ranges from headway setting 1, 2, 3, and 4. And you can see, interestingly, from the first glance, you're going to see that for headway setting 1, actually the speed variation is amplifies across the vehicles quite a lot. But for headway setting 4, the speed variations do not vary that much. So keep this observation in mind, and it has significant implications to energy consumption. For this experiment, due to the time, we didn't directly collect the fuel consumption from the vehicle, but we actually use some validated, well-known fuel consumption and emission models. For example, VT Micro, to estimate the fuel consumption and emissions. And so this is a well-known model, basically using exponential regression to obtain the relationships between velocity, the acceleration, and the fuel consumption and energy emissions. And so here are the results about fuel consumption with varying headways. So, so we can see actually we have 2 sets of experiments. The first set has the first lead vehicle at relatively high speed, and the second is lead vehicles at relatively low speed. And we can see from these experiments have fuel consumption, CO emissions, HC emissions, NOx emission. We can see overall, like, headway settings increases. This is headway setting 1, 2, 3, 4. As you see, from a headway setting increases from 1, that's shortest headway, to 4, longest headway, fuel consumption and emissions drop. And also, as the headway setting increases the box widths, that means the variation of the estimation also drops. All these are actually contributed, are attributed to the reduction of the speed variance as the headway increases. We also investigated the relationships between fuel consumption and emissions to headway setting and speed variance in this plot for both high speed tests and low speed tests. And we can see that as the speed increases, the impacts of speed variation on fuel consumption decreases. So if you compare the high speed test and low speed test, you see the high speed test in general has actually, as the speed varies, that the variation of fuel consumption and the relevant emissions are less than those for low speed tests. This is probably because at the low speed, that the speed variations will have a significant impact to the FCE and also fuel consumption and emission. FCE stand for. And they will have significant impacts on FCE measures at the low speed because speed is already low, But when the speed are at high speed, actually that's around, let's say low speed range. I forgot to mention that low speed range is about, I think, 25 to 35 miles per hour. And high speed tests are about 45 to 55 miles per hour. If you convert miles per hour to kilometers per hour, that could be, low speed could be like 40 to 50, high speed could be 70, 80, that range. So you can see at the high speed, and this is the range where the fuel consumption rate is almost optimum. So during this range, something like speed variation doesn't impact these measures a lot. So these are actually, what I presented here are actually our studies about field observations on fuel consumption and emissions. But we noticed that there is a very interesting relationship between the stability and the headway settings. And we also went further to analyze that theoretical relationship between the stability and a headway setting, as well as like safety buffer settings. So we came up with analytical models that rigorously specify the relationships between headway and the safety buffer, and we put that into a robust safety buffer model that ensures the safety buffer is just enough to have the following vehicle drive safe, regardless of the lead vehicle's driving patterns within a wide range. So interestingly, this model, although appearing as a very complicated nonlinear optimization model, actually this is linear optimization model, but it has differential constraints, differential equation constraints. It's very complicated, but we fortunately derived the analytical solution to the above complicated problem. That means that there is a direct mapping or functional relationship between some key parameter, and with that we can actually investigate some findings between mobility or headway settings and stability as well as safety. So basically headway settings, and we can theoretically show that as headway settings setting increases, the safety buffer will decrease, and as a result the traffic oscillation will be milder. That means that smaller oscillation amplification ratio, or actually control gain, and the longer traffic oscillation multitude. So these can be all linked as attributors to why FCE becomes less as the headway setting increases. So this could be attributed to another trade-off between the fuel consumption and emissions and headway settings. So regarding the theoretical analysis on the relative empirical validation, you can check on these two preprints. So I think I'm about to use up my time, and I think well, I just have one more slide. So insights is like proper AV headway setting management. We might want to look into how to make traffic stable and reduce fuel consumption and emissions, especially at low speed traffic from our analysis. In the future, I think we will look into some topics like in mixed traffic, AV plateau, and also, I have to point out the limitation of these studies. We're using fuel consumption models, but in the future, we can directly measure that from OBD data. And also, we may want to investigate not only internal combustion engine vehicles, but also electric vehicles in the future. They may have different energy consumption patterns. That's all my presentation. If I have time, I'll be happy to take any questions.
Okay, Xiaopeng, this is indeed a very interesting study to consider headway settings and speed information. For the headway settings should be affected by geometry information on highways. The desired headway should be a function of geometry parameters of that route section. So my question is, for your experiment, how do the geometry parameters look like? Are you using the most straight, flat freeways, or with different gradient curve freeways?
Yeah, that's a great question. First of all, headway setting is not impacted by geometry, but the actual headway is impacted by the geometry or driving states. Headway settings are just 1, 2, 3, 4 that are the buttons on the vehicle.
Yeah, the number is
yeah, it is just how the user specifies it, and regardless about the driving conditions. But the actual headways, if you measure headways, maybe the uphill slope would be different from a downhill slope. That's the first point. The second point is actually it's a really interesting study direction to look into how the geometries would impact fuel consumption and relevant measures, but we haven't investigated that in our experiments. In our experiments, the settings are all mostly level road with small curvatures. And on average, you can consider that as zero, almost close to zero horizontal and vertical curvatures. But in the future, it is important to investigate that, especially for heavy duty trucks. That impact is more significant, as I expect.
Sure. Okay. Any questions for Professor Li? And in the interest of time, we can it probably one short question. Okay, if no further questions, we will proceed to the next speaker, because just now two speakers contact me, and they are also assigned to this session, and we will have additional 3 speakers, Professor Yimin Bie and another 2 PhD students from Beijing Institute of Technology. And thank you, Xiaopeng, for your